Scaling a quantity like temperature is straightforward. If you double a room's heat, you get a single, predictable number. But engineering forces operate as vectors, carrying both magnitude and direction. When a bridge cable fails, that force acts along a specific line in space. Standard multiplication logic stops working when you attempt to multiply two different directions together. You cannot simply multiply one path by another and expect a traditional result. To navigate the physical world, mathematicians had to develop an entirely different operational logic for calculating how these interacting directions behave. When two vector forces interact, the spatial angle at which they meet determines the mathematical outcome. Because of this complexity, mathematics provides two distinct types of multiplication for vectors, depending on what information an engineer needs to extract. One method reduces two directions down into a single number, while the other generates a completely new direction in three-dimensional space. Mastering this dichotomy provides the foundational toolkit for calculating spatial relationships in the field of engineering. The first method is the dot product. Its algebraic definition multiplies the magnitudes of the two vectors by the cosine of the angle between them. This is a scalar product. It takes two directional inputs and outputs a single number, stripping away the spatial coordinates. A positive dot product indicates vectors working together at an acute angle. If negative, they oppose each other at an obtuse angle. And when exactly zero, the vectors are perfectly perpendicular. The dot product serves as a definitive test for determining if physical forces are aligned or completely orthogonal. The second type of multiplication is the cross product, which is used to define the three-dimensional space created by two vectors. Calculating this requires the determinant matrix method, using a grid to track how the vector components interact across different axes. Unlike the dot product, this calculation yields a new three-dimensional vector instead of a simple number. This new vector points exactly 90 degrees away from the original two forces, following a directional rule perpendicular to the plane they share. The magnitude of this vertical arrow is identical to the area of the parallelogram formed by the two original vectors. By dividing this magnitude in half, engineers can instantly calculate the area of the triangle formed between the two vector points. The cross product allows engineers to define and measure the geometric space occupied between interacting forces. Viewed side by side, these two products offer complementary outputs. One collapses space into a value, while the other expands it into a new dimension. The dot product remains the primary tool for analyzing force alignment and testing for perpendicularity. The cross product is used to generate new dimensions and calculate the spatial surface areas created by those forces. Ultimately, these mathematical operations provide a direct, precise language for solving the complex, real-world physical challenges found in modern engineering.